In this video, we're going to take a look at the mechanism for the reaction of elimination from a halogenoalkane. If you're following this in your notes pack, we're on page 11. Now, elimination is a reaction in which an atom or group of atoms is removed from a reactant. And because we're looking at halogenoalkanes, we need to have a think about the structure of our halogenoalkane. So I'm just going to scroll down a tiny bit and draw out the structure of a simple halogenoalkane. In this case, we're going to have a look at chloroethane. So to draw chloroethane, I'm going to start by drawing from the stem of the name eth and an alkane being saturated with a single bond. I'm going to draw out and put a chlorine onto my halogenoalkane. So here is the structure of a simple halogenoalkane, and we're going to eliminate a group of atoms from our structure. We're going to be eliminating the chlorine atom and from a neighbouring carbon a hydrogen atom, so we're going to eliminate a H and a Cl. Now HCl is an acid, so we're going to be using a base to undergo this elimination. Our reagent is going to be potassium hydroxide. Now, one of the things to be aware of when thinking about this mechanism is that potassium hydroxide was also the reagent for the nucleophilic substitution of halogenoalkanes, so you must think carefully about how we're causing these two reactions to be slightly different. It's all to do with those conditions. We're going to be changing the conditions from those we used for nucleophilic substitution, and we're now going to be heating, and that might be by reflux, which is a technique used in organic chemistry to heat without loss due to evaporation, in ethanol as the solvent. So when we got nucleophilic substitution, we were using warm aqueous conditions. We're now using hot conditions, and we're in ethanol. Now, if we have a look at our little instructions on page 11, it says to us that the halogen atom is always removed. Let's remove the halogen atom. This will be this atom here. And then it says the hydrogen from an adjacent carbon. Now, that means adjacent to the carbon that has the halogen. So we're going to the adjacent carbon and we're going to remove a hydrogen. There are 3 hydrogens on the adjacent carbon, only one of them will be removed. We're using KOH as our reagent, so we're going to put in our other reagent into our equation, and it tells us a double bond is formed between the 2 carbon atoms. So I'm going to draw the 2 carbon atoms. I'm going to draw out the structure of an alkene, and we can see that on the left-hand carbon we've lost a hydrogen, we still have 2 hydrogens. And on the right-hand carbon we've lost a chlorine, we still have 2 hydrogens. And we've got KCl and water as our other products. You should stop the video now, pause it, and have a go at carrying out that reaction with 1-bromopropane. Right. Have you had a go? If you have, you should have drawn a propane structure, which is 3 carbons, with a Br on number 1, and then we know that it's a saturated structure, 1-bromopropane, so we're going to fill in with hydrogens. We're using KOH as our reagent. So did you remove the halogen atom and then a hydrogen from a neighbouring carbon to form a double bond? Our right-hand carbon has lost the halogen, still has 2 hydrogens, and our left-hand carbon has lost a hydrogen atom, still has a hydrogen and a methyl group. And we're left with KBr this time, and water. We could name this alkene. This alkene is 3 carbons in a row. This is called propene. So again, pause the video again and see if you can have a go at the elimination from 2-iodobutane. If you've had a go at that, you might have noticed that you've got more than one possible answer here, because we can draw our 2-iodobutane. hydroxide. I'm going to change the use of the highlighters a little bit here because we've got two possible answers. So I'm going to have a look at eliminating the halogen, and for this first one I'm going to eliminate the hydrogen from the neighbouring carbon that's to the right. And so we've got two possible answers. This first answer, where we're eliminating the hydrogen on the right, is going to lead to our double bond at the end, two hydrogens and then a hydrogen and an ethyl group, CH3CH2, plus Ki and H2O. Whereas if I were to eliminate the iodine and then the hydrogen to the left, we're going to get a different product, because now the double bond is between those middle two carbons, and one of them on the left has a hydrogen and a methyl group, and on the right also has a hydrogen and a methyl group, plus Ki and H2O again. Now if we look at naming these two, we can see that in the top one we've got a 1, 2, 3, 4 carbon chain. We're going to call that but-1-ene. And the bottom one, we've also got a 4 carbon chain, but the double bond is now between numbers 2 and 3, so we have but-2-ene. One of the things you might want to remind yourself about at this point is the difference between the types of isomers. But-1-ene and but-2-ene are structural isomers of one another. They are position isomers, but also to remind yourself that a structure like but-2-ene can exist as both an E and a Z stereoisomer. And therefore there are a total of 3 possible structures that we might form. The isomer that I have drawn here is the Z version, because the methyl groups, the highest priority groups, are on the same side of the double bond. So what we're going to do now is take a look at the mechanism for this reaction. How does it happen? So we're going to go back to our first example where we had a nice straightforward halogenoalkane, chloroethane. And we're going to remind ourselves that our reagent was potassium hydroxide, but remember that we don't put metals in our mechanisms, so we're going to use just the hydroxide ion with its negative charge. And that hydroxide ion is going to go and use its lone pair. Remember that a curly arrow shows movement of a pair of electrons, to grab a hydrogen ion. Now when something accepts a proton, it is described as a base. So the role of hydroxide in this mechanism is to be a base. The pair of electrons in this carbon-hydrogen bond then are moved and form a new shared pair between the two carbons, and that would become the double bond. And the pair of electrons in this carbon-chlorine bond are moved onto the Cl to form a chloride ion. So we're left with double bond between the two carbons, having lost the hydrogen and the chlorine. Now the hydrogen went with the hydroxide ion to form water, and the chlorine gained a pair of electrons from the bond to become a chloride ion. The name of this mechanism is elimination. Pause the video now and see if you can apply that to the elimination of 1-iodobutane to form but-1-ene. Okay, if you've had a go at that, hopefully you drew out 1-iodobutane with the iodine on number 1. And all the rest of this is saturated. Hydroxide ion with its lone pair on the oxygen and a minus charge is going to go. And remember that the hydroxide is removing the hydrogen, and the hydrogen is removed from the neighbouring carbon. So iodine is on carbon number 1, we're going to carbon number 2 to remove the neighbouring hydrogen, Then we're going to break the carbon-hydrogen bond and move the pair of electrons that were shared in that bond to make the double bond. And then we're going to break the carbon-halogen bond and move the pair of electrons onto the halogen to form a halide ion. So we have ended up with a double bond between carbon number 1 and carbon number 2. And carbon number 2 has a hydrogen and an ethyl group left on it. And we've been left with some water and an iodide ion. Remember, our mechanism is named elimination. So pause again and have a go with 2-bromopropane. 2-bromopropane. Prop means 3. Meth, eth, prop. Remember, prop is 3 carbons. And we have got 2 adjacent carbons here, but both are identical because 2-bromopropane is symmetrical. So it wouldn't matter if you've gone for a hydrogen on the right of the bromine, that's fine. I'm going to go to the one on the left, as long as where you break the carbon-hydrogen bond corresponds to where you collected the hydrogen from. A little mechanism going on like that to make propene. Now, if you've drawn to the hydrogen from the right-hand carbon, you'll just have a picture that is a mirror image, a reversal of my structure. It is still the same structure, it is still propene. And the bromide ion, this is called elimination. So to finish off this little section, what we're going to do is compare the 2 mechanisms for reaction of a halogenoalkane with a hydroxide ion. So when we react a halogenoalkane with KOH, the product we get will depend on the conditions we use. So if we were to use warm and aqueous conditions, we're going to get a substitution reaction, and in that substitution reaction the OH is going to act as a nucleophile. It's going to donate a pair of electrons to a delta plus carbon, and the major product is going to be an alcohol. We're swapping the halogen for the hydroxy group. If we were to use a hot and ethanolic condition instead, so a lot hotter and dissolved in ethanol, then our OH minus is going to act as a base and accept a proton, and our major product is going to be an alkene because we have undergone elimination. So you can have a look on Moodle. I think there's a little example for you of the 2 different reactions, but you just need to remember it's all about those conditions. So don't forget that those conditions are going to determine which product you get.